Hi everybody, welcome to another video in Discrete Math section 1.3 propositional equivalence. So this is just equivalent between two propositions. So we have some definition here. Tautology, it is always true. Contradiction, always false. And contingency is neither tautology or contradiction, so could be true, could be false. Right, now determine if the following are tautology, contradiction, or neither. Right, P or not P. Right, so in that case, let's construct a truth table for it. We only have one statement, so it is true or false. And then we have the negation. Always do negation first before conjunction or disjunction. So this is just false, true, and now it's or. Right, now it's or. So it's true, one of them is true, so or is going to be true. So both of them true, so this is a tautology. Right, the next one we have P and not P is N. Only one statement, proposition, true or false. Now negate that, false or true. So this is N. It is true when both of them are true, so this case false. So what we have here is a contradiction. And this one not P, going to P. So false and true. Now not P into P. Right, so we go from here to there. Now implication or conditional statement. If true imply false, so true imply false here. Not P to P, true imply false. This is going to be false, and this is going to be true. So this is neither tautology or contradiction. So we call that contingency. So, of course, we can always use the truth table to tell if they are equivalent or not. Right, equivalent. To compare proposition P and Q are logically equivalent. We use if the biconditional tautology. We can use this simple. And when we do that, if the column they are equivalent, if the truth table giving their two values agree, so we just have the two statements are equivalent if on the truth table they have the same matching two false values. Right, so let's look at this example. Show that not P or Q is equivalent to P imply Q. Now this is important. On the previous section we say that we have and, we have or, exclusive or, and negation. But we don't have anything for conditional if we want to use a calculator. It's true, there's no direct operation, so we have to make some adjustment, and this is the adjustment that we need. Right, so I'm going to draw a table for this. I should have this in the note already. So P true, false, Q true, false. Right, first, of course, for this one, we're going to do the negation first. Not P. Just negate, not P here. So false, true. Now we do not P or Q. So right, not P or Q. So these two columns, and this is a disjunction, or is false when both of them are false. So this is going to be false because both of them are false. Everywhere else is going to be true. And now we just need to do the implication of P to Q. Right. So P to Q, true, and implication conditional is false when true implies false. So this is false. Everywhere else is true. And after all said and done, as you see, these two columns, they match in true false values. So because of that, the conclusion is that they are equivalent. Or we can write not P or Q equivalent to P imply Q. So now if we want to write P imply Q, we're just going to use this on the calculator. Right. Of course, the truth table will tell if the statements are equivalent. But of course, if we can do that without a truth table sometimes take some time to do. So there are a lot of rules that we have. But before that, something more most important of this rule, the De Morgan's law, is that the negation of a conjunction is the disjunction of the negation. So the negation would turn the V down to a wedge. Right, now we're going to do that on this table. We'll try to prove the De Morgan's law. Right, first P and Q. P, true, false. And then Q, true, false. And then the negation of both of them. False, true. Negation of Q, false, true. Right. There's quite a few here. So we're just going to do this P and Q. Right. P and Q. So this is the first two column, and this is N. So true when both of them are true, everywhere else are false. And now we just throw the negation to it. So just negate everything we just have. Right. Now we're going to do the right hand side. So the right hand side is the negation, the OR of the negation. So we have these two values. This is OR. So this is OR. It will be false when both of them are false. Everywhere else is true. As you see, they're matching now. So this is the proof for the first statement. Right, next we're going to do P or Q. So the first two here. Is OR. So true when both of them are true. Wait a minute. Yeah. I'm sorry, it's false when both of them are false. Everywhere else is true. Now we need a negation of that. So false, 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 and true. There's a typo. This should be a negation here. Sorry. So we focus on that. So this is not P and not Q. What was that? Yeah, it's N. So pretty much these two. So it's N. So it's going to be true only when both of them are true. Everywhere else it's going to be false. So true when both of them are true. And of course, once again, these two match. So what we see here is these two are the same. So which is the second equivalent relation here. And these two are the same, which is the first relation. Right. Of course, like I said, we can always use the truth table to confirm that the proposition are equivalent or not. But if we can do that without the table, it's even better. Right. Here's some of the laws. Any statement and true is going to be the statement itself, and any statement with false is or false is going to be that statement itself. Because if both of them are true, if P is true, then it's true. If P is false, then it's false. Right. That is identity law. And domination. If we're going to flip, this is false. This anything or true. Of course, we only need one of them two to be true, so that's true. And we only need one of them to be false for the whole thing to be false. So that's why we have called the domination of true in a disjunction and domination of a false in a conjunction. An important law. If we have a bunch of the whole statement are the same, if it is conjunction, it just the statement itself. Double negation. I think we talk about this in the problem of the identical twins. Negation of negation is the statement itself. And then we have the negation law. If P or not P is going to be true, because one of them has to be true, and that's enough for them to be true. Commutative law to interchange. Associative law, meaning that if we have a whole bunch of conjunction or disjunction, order doesn't matter, we can just do any two of them first and then just proceeding. And then associative law, right, distribution, if you will, and absorption law. And there's a lot of laws that have no names on it. Of course, you're not going to memorize all of them, but some of the basic, De Morgan's law, and one of the first few here. Right. Now, constructing new logical equivalents. So we say that if we can go with the sequence of equivalents, and we can trace back from the first to the bottom, if all of them are equivalent, then all of them are equivalent, meaning the first and the last are equivalent. Right. Now, I'll show that this is equivalent to that. Of course, if we have a true table, that's easy, right? But we're not going to use the true table here. I just use some of the intermediate step. Maybe we go from 1 sign to that sign. Right, so first of all we have this and this, so this is kind of distribution, right? So difference between the distribution and associative law is that those will be the same. Associative, let's go back and catch that when this copy and paste. So distribution is where we have a conjunction in with the disjunction, right? So this is what we have here. So it's going to be P or not P, then N P or Q. Right. So I'm starting from the beginning. P or not P, Q. Right. So this is distributive property. Now, P or not P, to P or not to P. Actually, it doesn't matter here because this is all. If one of them is true, then it's going to be true. So this one is going to be true. Sorry. Yeah, it should be that. Right? So, yeah. So distributive P to that and then P to that is true, and now if this is true, the whole thing is true. If this one false, the whole thing is false because it is conjunction. So actually the true here doesn't do anything. So we have that, and now this is equivalent to that, right? Now what is actually, this one is equivalent to what? Negation. This is the De Morgan's law. I think there was a typo. I think this should be a negation. Sorry about that. Otherwise, I would not need the parentheses for no reason. Sorry. So we have to. And by De Morgan's law. Of course, we can always use the truth table. So once again, negation of the whole thing. So that's why we need the parentheses. So when I type it, I forgot the negation. Right. So negation, we do inside the parentheses first, distributive properties, and then we have that. Of course, it's all, one of them is true, so it's going to be true, and this and both of them is true, and it's true. If it's false, it's false. So the true here is, we don't really need. And then finally, I will turn it back into De Morgan's law. Right, like I said, you can prove like that without using the truth table. Of course, the truth table certainly works too. Right, now show that this is tautology. Well, usually conditional statements are kind of difficult to prove. So you write the properties that is equivalent to the implication here. It's going to be the negation. And then or. So instead of write the implication, the conditional statement, Just going to write like that. Okay, right, let's start from the beginning. Right, so that gives us what? De Morgan's law here, negation of P, and we have to flip the V in wedge. So we flip it, and this is what we have. Now, all of them are disjunction, so we just say not P, not Q, P, or Q. Now we can just reshuffle, put the P and not P together. I mean associative properties and commutative. We just change the order because all of them are disjunction. It doesn't matter what order we do it. But this is all. One of this is true, so this is true. One of this is true, it's true. And finally, this is true. So because it is identically to true, so that is tautology. Right, propositional satisfiability. Right, a compound proposition is satisfiable if there exists an assignment of true values to this, so that is true. If we cannot come up with that, then it's going to be unsatisfiable. Right, so determine the satisfiability for the following. Of course, constructing the truth table for this is quite a lot of work, so we're not going to do that. So we're just trying to think. Right, so we look at this, and let's say we want this to be true, right? If this is true, then this has to be true, this has to be true, this has to be true, right? A conjunction is true when everything has to be true. So we have to say P or not Q, this have to be equal to true. I'm just going to spell it out. Q or not R have to be equal to true, and R not P have to be equal to true. So we have true all the way. Now, the thing with this is we need this is all, so we only need one of these to be true. If P is true, then it's good. So let's say if P is true, if P is true, then this one is true, it's good. Then this one R has to be true, because if this one P is true, if P is true, then the first one P is true, then not P is going to be false. In order for this to be true, R has to be, then R has to be true. If R is true, then not R is going to be false. And for this to be true, Q have to be true. So that would come up with an example. Right? So once again, if it's true for the disjunction, one of them has to be true. So let's say P is true. If P is true, then not P have to be false. Then R has to be true. If R is true, this is not then Q. If R is true, then not R is false. Then in here, Q has to be true. So this is a condition that makes this one satisfiable. Right. Next we have this. Once again, kind of difficult when we look at this. So I mean in conditional statement. So if we rewrite this as not P, I'm sorry, not, this is conditional, so we just write this as not or and then this is not P, De Morgan's law. Right, we see this one before, right? Not P or P, that's true. Not Q or Q, that's true as well. Right, true, true, and that is true. So we have between true or true, which is true. So we have negation of true, which is false. So it doesn't matter what we choose, it's going to be false. So this one is unsatisfiable. Doesn't matter what we choose for P or Q, it will not work. This one is satisfiable if we choose P to be true, R to be true, and Q to be true, and that certainly works. Right. With that, we finish section 1.3 here. I see you in another video in this week math. Thank you for watching.